Okay guys, I'm going to show you the setup for Lab 9, the series parallel analysis. In order to do this, we need our multimeter, we need our breadboard, we're going to need three resistors. The top resistor is a 330 ohm resistor, the middle one is a 120 ohm resistor, and the bottom one here is a 22 ohm resistor. Your first step before putting these in the circuit is to measure the resistance. I'm going to set this up and show you how that measurement works on there. Okay, looking at the measurement for the 30 ohm resistor, we have on our meter 0.326 k ohms. 0.326 k ohms is 326 ohms. Now we'll switch it up and look at the 120. Okay, looking at the 120 ohm resistor, we have 0.119 k ohms. I can actually change the range on this to be a little more accurate. Changing the range, we have looks like 100. Well, now we're reading 120 ohms exactly. 120 ohms exactly for our second one. And for the 22 ohm resistor, we are reading 23.8.78, flipping back and forth there. Here we are on the 200 ohm range to be the most precise measurement. Now we're going to set this up into our circuit. Give me a moment. I'm going to put that onto the breadboard here, and then we'll explain that setup. Okay, circuit setup is as follows. On the left side, we have our 120 ohm resistors right here. We have our 330 ohm resistor right here. We have our 22 ohm resistor right here. This is the positive bus line, and it's going to get its power here. And this is the negative bus line. That power line would come in right here. So when we're looking at the circuit, we see a circuit split to parallel. So this is our parallel branch, resistor 1, resistor 2. They share a common node right here. That common node, they come together and then in series through the 22 ohm resistor and back to source that way. So our first measurement that we need to take is the total resistance on this. I'm going to change my ohm meter here. Well, actually we can be in the 200 ohm range because we expect 110 ohms as a total resistance measurement. What I've done is I've hooked the negative onto the negative bus line there with that alligator. I can then touch my input source lead here, look at my meter. I have 110.5 ohms as a total resistance measurement. 110.5 ohms is a total resistance measurement. Okay. When we're looking at individual resistors in the circuit, the parallel resistors are going to give a parallel equivalency, and if we break that down, measuring my meter here, we'll move to our parallel branch. If I measure the one resistor, I'm actually measuring them both, and I have 88.9 ohms. It's pretty close to our predicted 88 ohms. When I'm looking strictly at my series resistor and I'm measuring within the circuit, I should measure close to the 22. We're getting 23.7 ohms as we break down our circuit. Okay, next step is to take some measurements with power as we complete our reap table. Give me a moment to set the circuit up for that, and I'll come back to you. Okay, so we've got our power supply set up here. Our current knob is up. You can see my analog gauge there is set pretty close to the 9. We're between the hashes there between 9 and 10. And I actually made it more exact. My voltmeter is set to measure DC volts. I'm on the 20 volt range, as we're more than 2. And we're going to come down here with my positive probe. I have my negative probe connecting it in with that yellow alligator there. So I can measure my source voltage here and accurate set it. We got it set at 9.01, flipping back and forth, 9.01, 9.01 is where we're at as our source voltage. So reading 9.01 there, come back to my circuit here and take a couple measurements. If I'm looking across the whole circuit, I should still see my total voltage, and actually we're right on 9 there. And now if I switch nodes to what would be my B node, and now all I'm doing is looking between the negative ground, and I only have resistor 2 in here. With resistor 2 in there, my reading is 1.83. Let's look at the parallel branch only. I'm going to move my alligator, set it right here, and put my positive probe here, and I'm looking at the parallel branch. Looking only at the parallel branch, we have 7.16. Pretty close to the predicted parallel equivalent drop of 7.2 volts. So we're able to see Kirchhoff's laws applied here when we're dealing with voltage. I'm going to change my meter here and set it up to measure current, and I'll show you those readings as well. Okay, so my meter is now set to measure current. See, my red probe is in the A slot. I am on the 200 milliamp scale. We're expecting 81.81 milliamps in this circuit. What we've done here is I have my positive source coming in right there. My negative source is connected to the negative probe to my meter. So the negative source comes in the negative probe to the meter. It goes back to the meter, through the meter, comes to this positive probe, which I'm going to connect to my negative bus line there. When I do that, my reading is 81 point, fluctuating around 81. I guess we can call that 81.6. 81.6 is the total current as measured. Now, if I flip my probe and put it on my series resistor right here, I should still see 81. Well, it's jumped a little bit, but I see about my 81.8 is the current there. So basically my total current, whether I'm measuring from the source end here, which actually is 81.8 there, I'm getting the same values for the series resistor, and that makes sense. That's Kirchhoff's law. We're going to adjust the circuit here, and we're going to look at the parallel branches. Okay, what I've done is I've switched my alligator to alligator up just so I have a free hand here. It is going to my positive lead on my meter. I have currently lifted the downside leg there of resistor number 1, our 120 ohm resistor. With my negative probe and the power on, I'm going to connect node B. That's the junction of where these guys all come together. Okay, and when I connect node B and then go and read my meter, I should see a measurement close to, let's go look up here. So we're fluctuating around. Ideally this should be about 60. We must have a little more resistance in our yellow alligator. I'm seeing 57.8, but that could be a legitimate reading there. 57.9 is the current going through resistor 1. Again, there is some resistance in our wires here, so might throw us off from our calculations. To change this and look at resistor 2, I have to lift resistor 2 out of its hole. I have to plug resistor 1 back in to the circuit itself. I'm going to switch my alligator up so I'm on the back end there, and then connect back into node B. So now I'm looking at resistor 2. Resistor 2 is showing 21.6 milliamps, and that is, as we predicted, 21.8. So we're pretty much right on there with our branch currents. What this is showing us is that the Kirchhoff's law is true. The parallel portion splits the current proportionately by the resistance. The path of least resistance gets more current. This is a bigger resistor. This is 330, so it gets less current. Those two currents come together, and they continue on through this resistor as our total current of 81 some milliamps. So we were able to prove Kirchhoff's law with this lab, and this also proves the calculations we made in class. And just a pan over here to the classroom board. This is what we did today. Your calculation table should be somewhat similar. So that is our series parallel lab.